So when we talk about the different types of electrolytes, okay, we're talking about 3 specific types of substances, okay? Those 3 types of substances are acids, bases, and salts. We've talked about acids and bases before. We learned how to use pH paper. We learned how to use litmus paper. Okay, some of us may have even done a lab with cabbage juice as an indicator to determine the pH of substances. Okay, we're going to talk about pH after we talk about these 3 types of electrolytes. Okay, now my goal here is for you to be able to look at any molecule, and we know that a molecule is 2 or more atoms, right, mixed together or combined together either ionically, which is a giving and taking of electrons, or covalently, which is a sharing of electrons, right? My goal for you is to be able to look at any molecule, whether you know what the name of that molecule is, and to be able to determine whether it is an acid, a base, or a salt. Because there's some real key features, okay, or hints as to whether something is going to be an acid, something is going to be a base, or something is going to be a salt. Okay, so we're going to start off with acids. What do we know about acids? We've looked at acids before. Okay, what do we know about acids? They belong somewhere specific on the pH scale. Where do they actually belong? At the top of the scale or at the bottom of the scale? They belong at the bottom of the scale. Something that has a low numerical pH, so a pH of 1 or 2 or 3 or 4, 5 or 6, is considered to be slightly or very acidic, right? Now, we're going to talk about pH later. Right now, we're going to look at what it is that makes something acidic. Something the reason that substances are acidic is because of their high concentration or their high presence of hydrogen ions, H+. Okay? When there is a lot of hydrogen ions in a molecule, or if there is a substance that's made up of molecules that has a high number of hydrogens, it becomes acidic. All right? Case in point, something like HCl. HCl is a liquid substance known as hydrochloric acid. Okay, it's the combination of hydrogen, which has 1 valence electron, and chlorine, which has 7 valence electrons. So the chlorine takes that electron from hydrogen and it makes a real nice stable molecule. But in a substance, in a beaker full of hydrochloric acid, you have a lot of hydrogen ions. Okay, you've got a lot of H's. Whenever a molecule has a lot of H's, we say that it is an acid. And the H's usually appear at the front of the actual chemical formula. Okay? Something like sulfuric acid looks like H2SO4. Okay? You don't need to know that that's sulfuric acid right now. You just need to be able to look at that and be like, there's some H's. I bet you that substance is acidic because of the presence of those hydrogen atoms in that combination of atoms that make up that molecule. Okay? So when we look at something that's acidic, if I were to give you a list of a variety of different molecules, the big hint to see that something is in fact acidic is that it has hydrogens in its chemical formula, and they are usually at the front. They're always at the front. Okay? The only exception to that is a substance that you know quite well, or one of the major substances that don't abide by this guy. Okay? That is not acidic. All right? That's the only exception to the rule here. Water, though, when we actually start playing around with acids and bases later on, water also becomes very important in these types of reactions, and we're going to see that, okay, later. But right now, when we're talking about identifying acids, we're talking about there being a high presence of hydrogens. Okay, hydrogens, and they're usually always at the front of the molecule, with the exception of water. Okay? Bases, on the other hand, also have an identifying little molecule that's always attached to them. All right? Bases tend to have something called a hydroxide ion. Okay, a hydroxide is a polyatomic ion, which means it's stable. Okay, it's considered one unit even though it's actually got two atoms stuck together. All right, we don't have to learn about polyatomic ions. All right, that's not a topic in our course, but when we talk about things like carbonate and phosphate and all of these 8 molecules, okay, a lot of those are called polyatomic ions. They're quite stable, even though SO4 here is a combination of sulfur and 4 oxygens, it's stable as one unit. That is actually another example of a polyatomic ion. But don't worry about those, okay? What I want you to notice here is hydroxide. Hydroxide is always an oxygen combined with a hydrogen, but the oxygen always comes first, okay? Even though it's called hydroxide, and we pronounce the hydrogen in that first, just the way it is, okay? Now, the interesting thing about hydroxide is quite basic. And when you add hydroxide to an actual metal or a combination of atoms, it gives it that basic behavior. A good example of a base is NaOH, okay, sodium hydroxide. The identifier here that makes this basic is the OH, and the OH is usually at the end. Whereas with acids, the H is usually at the beginning. With bases, hydroxide is usually tacked on to the end of the molecule. Okay? An example of that would be something like, and let's look at this. This is kind of a review from last year. If we've got Mg bracket OH bracket 2, that actually means that we've got something called magnesium hydroxide. Magnesium is in what group on the periodic table? 2. It's in group 2, which means it has 2 valence electrons, right? So it's got 2 electrons in its outermost shell. Yeah? If we look at hydroxide, hydroxide has a -1 charge, which means it's missing 1 electron in its combination. And if you think about it, that makes total sense, right? Because hydroxide is oxygen, right? Which has 6 valence electrons, so Lewis structure here, 6. With the hydrogen, that only has 1 valence electron. So what's my total number of electrons there? 7. I only have 7 electrons. How many am I missing? 1. I'm missing 1. I'm -1. I need 1 more electron. So that's why we say that hydroxide has this negative charge to it. It's missing 1. Okay? And hydrogen on its own has 1 valence electron. It's got 1 extra because 1 is never stable, right? In that first orbit, what is a stable number? 2. In the first orbit, the maximum number of electrons you can have is 2, right? Hydrogen only has 1, so it's got plus 1 electron, okay? So when we look at magnesium hydroxide here, if magnesium has 2 electrons, okay, in its outermost shell, it's got these 2 electrons hanging out, we have to have 2 hydroxides bind to that because each of them is going to take 1 of those electrons, right? Each hydroxide has a -1. So if you put 2 of them there, that gives you your 2-. That makes this a stable molecule, right? This is almost what this is. This is an example of ionic bonding, but it is ionic bonding with a compound as opposed to an individual atom. Remember when we did sodium chloride, where sodium has 1 valence electron, chlorine has 7. So sodium gives its electron to chlorine. They bond together. They're stable. It's a give and take. When they break up, they don't take back their actual electrons, right? They don't give them up either. So the same thing happens here. That's the reason we actually have an OH with a bracket and a 2 next to it. Because in order for this guy to be stable in the actual chemical makeup here, you need 2. But the key here, the key is that, oh, look at that, there's an OH. As soon as you see a big O and a big H stuck together, that should tell you that that substance is basic. And that should appear at the end of the molecule. Okay? So far, hydrogens just have H's. Right? Acids just have H's. Hydroxides have OHs. Bases have OHs at the end. Right? Which brings us to our last one, salts. And salts are things that you have actually seen for a very, very long time. You saw these last year. A salt is any time you have a metal bound to a non-metal. Okay? Anything that is metallic bonds to anything that is non-metallic. So in the case of calcium, which has 2 valence electrons, and chlorine that has is missing 1, it's got 7. Okay, this is a salt. Just like this is a salt. Okay, this Al2O3 is a salt because it's always a metal bound to a non-metal. The metal always comes first. All right? So when you look at identifying these 3 types of electrolytes, there's 3 tricks for you to look for. Number 1, if it's got hydrogens, capital H's, in and around the beginning of the molecule. So it's got H something, something, something. H something. That is an acidic substance. Okay? It's an acid. If you have a non-metal that is bound to an OH, or you have a molecule, something, something, bound to a big O and a big H, tacked on together, at the end, that's a base. If you have a metal and a non-metal bound together, it doesn't matter how many of each you have, but if you have a non-metal bound to a metal, then it is a salt. Those are your 3 types of electrolytes.